Okay, now should get enough people around, I hope. Any of them? Not many. Nine. Okay, let's start in the meantime. Okay, so good morning to everybody. Today we should keep saying something about the circuit that we studied last time. Basically, what we saw last time was this Fairchild MUE 723. It is a chip, a bipolar chip, based on BJTs and one JFET, that is used for creating a simple but powerful, in terms of performances, power supplies, series pass transistor power supplies, like this. Now I want to show you how we can use this chip for creating real power supplies. In particular, I just want to remember that this block here that I copied in all the slides, the following slides, is a simplified block diagram of what is inside the chip. So basically we have a Zener reference, a voltage reference amplifier that basically is able to give a voltage reference with some output current, that is 15 milliamps. And then we have an error amplifier. Basically, it's a very simplified differential amplifier, operational amplifier, sorry. It's only a differential amplifier made by two transistors. And then what we have here is the series pass transistor, basically Q15. Just don't consider this a Zener diode. We also have a transistor that can be used for current sensing, so in order to prevent the circuit from being destroyed by short circuit at the output. Okay, well, the chip is very stable, can give up to 150 milliamps if we use only the internal transistor. But if you put an external transistor, we can go for much higher currents. The chip is able to work with a single power supply up to 40 volts, but definitely it can work starting from something like 7 or 8 volts up to 40. I'll say even 10 volts because we have to energize, let's say, the Zener diode. So we need more than 6.2 volts, definitely. So I will start from around 10 volts up to 40 volts. Okay, now that we know what is inside and we know the block diagram that is here, I want to show you how we can use this chip for doing power supplies. Probably it's better if I start from this chip here, from this second example. Yeah, it's safe. So let's suppose that we want to make a power supply using this chip that is able to send at the output something between 7 and 37 volts. Obviously, when I say something between 7 and 37, I must say that the input voltage must be larger than the voltage that we want to send in the output. If we, for instance, we want to use 37 volts, we need 40 volts, 38 or 39 volts at the input voltage. If we are going to use it, okay, don't panic, okay, it should turn on again. Cigarette? Okay, yes. I don't want, okay. So, for instance, if I want to get 7 volts, I can use something like 10, 12, 15 volts at the input. That is also a good reason for reducing the dissipation in the series pass transistor. Okay, so the output voltage, the input voltage must be comparable, close to the output voltage if I don't want to waste a lot of power. Anyway, let's suppose that here, we don't know, we have 15 volts and the output is 7, 8 volts, but it's not that important. What I want to show you is that how the system is connected in order to get what we want. In particular, this circuit here has also a constant current limitation. So they implemented also the constant current limitation. Do you remember the constant current protection was the protection where we placed a resistor in series with the output. And what I want to do here is simply to follow the wires and check if it is something that we have already seen or not. Well, first of all, when we say V-in, that V-in is the voltage that goes to V+. V+ is this terminal here that is used for supplying all the blocks that are inside the chip. But also, we connected this wire here. That's a bit wrong because actually this VCC is the VC that is indicated here. Actually, we should write, I don't know if I can do that. This terminal here is not a simple VC, but is VCC. No, it doesn't work. Oh, sorry. This is VCC. Okay, that is the terminal connected here. So we are connecting to the power supply both all the supplies of the blocks and also the collector of the serial pass transistor, as we did in the past. Next, well, V minus, pin number 5, is simply connected to ground. Nothing special. Then we have what? We must bring the reference voltage to the error amplifier. For doing that, you see, we connect the Vref to the non-inverting input. So this wire here, Vref to non-inverting input, practically connects the pin number 4 to the pin number 3. There is a resistor for connecting these two wires. Please forget that for a while. Okay. Just imagine that we have a wire connecting the V-reference, the output of the reference voltage, to the non-inverting input of the error amplifier. And that's made by this wire. The resistor will tell you something more later. So this part is working. Then, if you remember, the error amplifier that in our previous schematics was a simple transistor. If you want, I can jump back and show you what was the schematic that we studied. Sorry for doing this mess. So I'm referring to this simple schematic here, the simple, this one. So in this schematic here, if you see, apart from the filament, and we had the collector of transistor Q1 connected to the power supply, and in that case, the input of the blocks, the supply of the blocks was this wire with R3. Then we had the reference voltage that was sent to the one input of the error amplifier, the transistor Q2. The other input of the error amplifier was the base of Q2, was connected to the voltage divider that sampled the output voltage for checking if it was okay or not. So if I go back to our circuit, integrated circuit, well, what we have here is what? The output of the series pass transistor is the emitter of the transistor. So this pin 6. And pin 6 is going directly to the output. We have also the series pass resistance for verifying the short circuit. But again, forget for a moment this resistance here, RSC. So that is the regulated output. That is simply the emitter of the series pass transistor. From the regulated output, we have a voltage divider, R1 and R2. That is the voltage divider that fixes the output voltage. The intermediate pin of the voltage divider is the one that in the past went to the base of the error amplifier. Now it goes to the inverting input of the error amplifier. So that is the inverting input, pin number 2. and is connected with the central pin of the voltage divider. Okay, so the basic schematic is there. We have a few more things. We better have a look at the part regarding the current sensing, and so the short circuit current protection, that in this case is a constant current protection. What we did in the past was to put after the emitter, the output of the series pass transistor, a small series resistance, and depending on the output current, if the voltage across this resistance was higher than 0.6 volts, we were able to activate a transistor. So if you see here, the left pin of the resistance is connected to CL. It's called the current limit. Basically, it's the base of the current limiter transistor, or sensing transistor here. So we have a connection to the base of this transistor. Then the 0.6 volts must be applied between the base and the emitter. So actually the current sense pin, the emitter of the transistor, is connected, you see current sense, directly at the output. So it's the same schematic that we used in the past. If the transistor activates, it will draw some current that usually should go to the base of the series pass transistor. In this case, the current is taken away from the current limiter, and so it reduces the biasing of the series pass transistor. So it's working like we saw in the previous circuit. There are two strange components. One is the resistor R3 that I told you to neglect for a while. But we have also a C1, a small capacitor, that's 100 picofarad. Why is that used for? Let's see where it is connected. It is connected between the inverting, well, the central pole of the voltage divider, that is this point here. Basically, it's the input of the inverting error amplifier. So it's connected between pin 2 and the compensation, frequency compensation pin, that is this one. So we have a capacitor connected between here and here. Okay? This is a capacitor connected between the output and the inverting input of an amplifier. So basically, this is going to implement a low-pass filter that is used for limiting the band of the error amplifier, or what we will say is used for frequency compensation of the feedback amplifier. So basically, this is pushing to lower frequencies the pole of the frequency amplifier, the error amplifier, in order to avoid any oscillation in the circuit. And it's basically looks a lot like a low-pass filter. Or if you want, we can also remember that when we have an impedance, a capacitor connected between the output and the inverting input of an amplifier, we are using the Miller effect for multiplying the value of the capacitor times the gain of the error amplifier. So instead, actually, we are using 100 picofarad, but it is like using, let's say, 10 nanofarad capacitor there, just for pushing at very low frequencies the open loop pole of the amplifier. And it stabilizes everything. Some time ago, when we were able to go to the lab, and we mounted something like this, actually we mounted a circuit which was made with the 2 transistors only. In some of those circuits, we were not able to do some measurements. We had strange output voltages that was not connected to our design. When we checked the circuit at high frequency, we saw that there was a very strong oscillation. And so, actually, if you use the tester, a voltmeter, for digital voltmeter for measuring the output voltage, it was unable to read the correct voltage. We applied the capacitor like this for limiting the open loop cutoff frequency, and so everything worked fine. In some circuit, it was necessary. In some other circuit, it wasn't. It depends a lot on the performances of the device. So, the last thing that I want to tell you about the R3 reason, why are we using this R3 resistance here? Well, we must remember that our error amplifier is basically a differential amplifier, okay, made with 2 transistors. But even if we consider it as an error amplifier, operational amplifier, we must not neglect that in real operational amplifier, we have bias currents in the 2 inputs. So there are those bias currents. In this case, it's quite evident that these bias currents are the base current of the 2 transistors. Well, once that we have bias currents, we may have problems due to the bias current itself. They can give an offset in the output voltage. If you remember what we studied in the past, the trick for avoiding any problem with bias current was to have the same resistances on both inputs. On both? Inputs. So we needed the differential amplifier inputs should see the same resistances on both of them. If they see the same resistance, it works fine, and we bring to 0 the effects of the bias current. Well, what is the resistance seen by the non-inverting input? If we see here, the inverting input first. Let's study the inverting. The inverting input is connected to the voltage divider. So if we consider the dynamic behavior of this circuit, and you look from the input, you will see that you have resistance R2 connected towards ground. The resistance R1 is connected towards the output. But if we bring to 0 all independent voltage sources, we can consider that also R1 is connected to ground. Basically, also because in the output there will be maybe a capacitor with a very which acts as a shortage to ground. Okay. No, simply, what is the impedance seen by the inverting input? We have resistance R2 connected to ground, but also R1 connected on top to ground. So basically, what we see from the inverting input is the parallel of R2 and R1 towards ground. And that is what the input bias current sees. If we want to null the effect of the bias current, also the non-inverting input should see the same resistance. Actually, it is connected towards Vref, that is a stable voltage, and dynamically can be considered as a ground itself. So R3 must be the parallel of R1 and R2. In this case, we have null effects due to the bias current. You see this formula? That was taken from the data sheet. They suggest, for those who don't understand electronics, let's say, that R3 must be the parallel of R1 and R2. So that's a good suggestion, but we know why. We know why we should take this, okay? It also says for minimum temperature drift. Why? Because certainly the 2 input transistors will have a drift. If they are not well balanced, we can increase this drift. Why? If they see the same resistance, the drift will go to 0. In this case, it is interesting that the output regulated voltage, and I hear strange noises. I suppose it was my PC. No, it's not. The poor PC. What is also interesting to notice here is that the regulated output voltage must be higher than the reference voltage. You remember the formula for the output voltage in our power supply with 2 transistors? It was something like that was VZ plus, in that case, was VB times the reverse of the partition ratio, okay? So R1 plus R2 over R2, something like that, I don't know. Okay, so this means that the output voltage will be larger than the reference voltage. That's good, but what happens if we want an output voltage that is lower than the reference voltage? We did not examine that case, but here that people from Fairchild must sell this chip to everybody. They must find a trick for using this chip also for output voltage lower than the reference voltage. By the way, that's the reason why in this particular configuration, they say that the output voltage must go from 7 up to, we don't care, okay. 37 is just due to a limitation on the 40 volts of the maximum voltage, okay. But they cannot go below 7. This means that 7 volts is the VREF. If you go back, they say VREF is 7.15. So that's the point, okay. There is another way to work. And that's why I'm showing you that later. Instead of sending as a reference the whole VREF, we'd use a voltage partition here for reducing the VREF. So what we send to inverting input is not VREF as we did in this case, but we are sending a voltage that is a part of the reference voltage. Okay, so first we use a voltage divider for reducing this voltage, and we use this as a reference voltage for our purpose. In this case, as you see, we are now able to have output voltage between 2 and 7 volts. Anyway, the input voltage here must be at least 7 or 8 volts, even if we want to use only 2 volts, because we must turn on all the electronics. In particular, we must turn on the Zener diodes that was at 6.2 volts. So I would say that here we need at least 8 or 9 volts, even if you want to use 2 volts output. So the difference is this. We first use the reference voltage and we create a reduced reference voltage. We can use 2 resistors. So we take some current from the reference output. But we can do that because in the specification, they say that we can take up to 15 milliamps from the reference voltage output. So we are able to draw some current from the reference voltage without changing the reference voltage itself. Okay, so we can use 2 resistances. Maybe we just design the resistances for having just 1 milliamps, something like that, so we don't charge. The point with resistances is that actually, we'll see that later, but when you let some current flow through resistances, you make noise. Current through resistances generates noise. So if you want to reduce the noise, in this reduce the reference voltage, we must use a capacitor that filters the high frequencies in the noise. And also stabilize a bit more the output. We are creating a sort of low-pass filter for having a very stable, reduced reference voltage. And we go to this input here. Obviously, at this point, we can connect the inverting reference directly to the regulated output. Well, I say directly, there is still resistor R3. Again, we want to put a situation where the 2 inputs of the error amplifier see the same resistances. So the non-inverting inputs sees the parallel or R1 and R2. So the inverting input must see the same resistance. That's why R3 is the parallel again of R1 and R2. Okay. We still have the compensation capacitor here, but also we have a short circuit. So all the rest of the circuit is remaining the same as before. We didn't change anything. We just used a trick, a particular trick on Trucchetto, for reducing the reference voltage using this partition, voltage divider here. So in this case, we can still use the same chip also for these purposes. Okay. Now, I like to show you how you can pass from the block diagram of the chip to the real operating circuit. So these are circuits that if you mount them, they work perfectly. No problem. I'll very quickly show you some other application. Well, maybe just the first one. Oh, this was something that they just wanted to save money. I don't know why. In this situation here, what they did was to use an external transistor that is called connected in series with the series pass transistor. Basically, this transistor, the internal transistor plus the external transistor, generates a Darlington transistor. And that is used for increasing the current capabilities of the circuit. It doesn't say much here, but you see, at least it says here, load regulation with 1 amp. So we passed from 150, let's say 100 milliamps of normal output to at least 1 ampere. It depends on the transistor, how big it is, it can give you more current. If you want much more current, you can still even use a Darlington here. So you can go up to 10 amps or something like that. I have at home a small power supply which works up to 3 or 4 amps using this chip here and an external transistor that is screwed on the box, a metallic box. So it can dissipate a lot of power. All other parts are exactly the same as the previous circuit. They even removed the remember R3, the resistance between the reference voltage and the input voltage. Maybe just maybe that the performance of this circuit are a bit worse than the previous. Why? Because it's giving so much current that you don't care anymore about the precision of the output voltage. So you can also neglect the resistance that's 1 cent of euros. They are saved money. That's okay. Anyway, it works. Okay. In this case, it's giving us, yes, 15 volts for the output. This is a bit more complicated. I'll skip this for a while. Instead, I want to focus on this implementation here, where they were able to use a fallback circuit for current protection. If we have a look at the circuit, this circuit here, on the left shows a voltage divider connected to a non-inverting input. This means that it should work with an output voltage below 7 volts. Actually, it says 5 volts, you see here. So we want a output voltage of 5 volts. Maybe this is a power supply for a large electronic digital card, some big electronic digital circuit. So they wanted 5 volts output. And so they had to reduce the reference voltage, but that's another problem that we already saw. What I want to show you instead is how they changed the sensing circuit. If you remember, what we did for implementing the fallback current protection was to use the series pass resistance first, but also we didn't connect the base of the transistor directly to the emitter of the series pass transistor. We use the voltage divider, that is this one here. So in the fallback protection, there is a second voltage divider that is used for scaling the variation in the output voltage. And these variations are sent to the base of the transistor. Then we have the sensing resistance that is connected between the output and the emitter of the sensing transistor. That is here. If you compare this schematic with what we saw in the past, you will see that they are the same schematic. Here, we don't have any voltage partitioner to the input, inverting input, so it is connected directly to the output. And it's fine. Okay. Okay, for instance, they don't say much about the knee current. of this circuit. But what they say is that using the resistance shown here, you can have a short circuit current of 20 milliamps. So it's very small, and is useful for protecting the series pass transistor. Maybe the knee current will be something like 100 milliamps. In this case, we don't have the output, the external power transistor like this one. So probably we are using the chip itself for its maximum current. So I would say that maybe the knee voltage is around, say, 100 milliamps, but the short circuit, the knee current is 100 milliamps. The short circuit current was reduced to 20 milliamps. So it is a good reduction. We protect the transistor. I don't know if you have a question about those circuits, also from home. Otherwise, I'll show you something different. Oh, prego. Come? Prego. C1, C1 is again the compensation transistor capacitance. So again, it is not connected to the inverting input, simply because the inverting input is connected to the regulated output, so it's already grounded, dynamically grounded. So at this point, they connect it towards the ground. It's useless to connect to here. This means that we are not using the Miller effect, basically. So we lost something, problem. Oh, you see here, they increased the value. Now it's 1 nanofarad. Because we are not using the Miller effect anymore for amplifying. So they started with a higher capacitor here. That is 1 nanofarad. Okay. What's next? I always forget. Siamo arrivati. Facciamo cose. Sì. Allora, sorry. Already I told you something about this chip here, the L78X6 series. This, for instance, is made by ST Microelectronics, but the same series is made by everybody. So you'll find in the catalog of any fabricator of a linear chip, like On Semiconductor or Analog, or any company that makes analog chips, will produce its own series of L78 chips. As I told you, those are very nice chips, because if you need only a fixed voltage, for instance, 5 volts, because you need this 5 volts for a digital circuit, you don't need to build the whole system like we did with the discrete transistor. No, we used what we studied before was a 2-transistor power supply. And so you needed to buy transistors, Zener diode, resistances, and then we need to make a big circuit board for soldering all the components. Or you could do that with the Fairchild, the MOA 723 chip, but again, you still had to solder a lot of components. If you don't want to waste time because you just need the fixed voltage, you just buy this 3-terminal device that looks like a transistor, and that's it. You need just very simple components that I'll show you later.
So it is useful to have a standard?
Yes. I do. For instance, here, if I want a 7805, that is something that gives you 5 volts. I can buy it in the TO220 package. That is this one, looks like a transistor. You just send the input voltage to this input. You solder the ground to the ground, and you have the output voltage in this pin here, and that's it. Something that I would like to let you know, you see the central pin. The central pin is ground. Look here. I'm sorry that when I zoom, it deactivates the laser. Anyway, can you see the hand from home? At home, can you see this hand moving? Si vede? No, here we can see it, but I don't know if
No.
No. Okay, so anyway, look at this ground that is on the left of the hole. Now I go back to the zooming. I'm considering this point here. What they say is basically that the metallic part, this metallic part here, is connected to the central pin of the package, to the ground. That is done because using a screw, we will screw this chip on a large heat sink, or we can screw this chip on the metallic box of the power supply and using the metal box for dissipating the heat. So if the central pin, sorry, just one moment, Firetto. Sorry. Pronto, signor Firetto? Buongiorno, salve. No, sto facendo lezione qua, sono in aula 140. Niente, le volevo dire, per questo pomeriggio salta, tanto per cambiare. Ok, sì, esatto, infatti l'ho detto ieri a lui questo. Poi ci sono buone notizie, la settimana prossima forse possiamo attaccare. Ok, quindi per martedì, poi le racconto, ok? Adesso sono lezione. Una buona giornata, arrivederci. Okay. So this is very useful because if you want to connect the transistor, the power supply, screw it directly on the box. We don't need any isolation between the chip and the box because all the boxes in our equipment will be connected directly to ground. So if the chip itself is already connected to ground, maybe we can still, we don't need any isolation between the chip and the metal boxes. Be careful that in some situation, this central pin for this package can be connected to the input or to the output. In this case, you cannot screw the chip on the box because we will create a very big short circuit. In this case, you need to use some spacer, some isolators that now are made by, basically by silicon, I mean a sort of silicon plastic that is able to conduct the heat but is isolated electrically the chip. In the past, they used the so-called mica. I don't know if in English it's called, it's said also mica. Mica is a particular rock that comes out in very thin layers. Is something that resembles, well, I don't know if you can see, this telephone here has a cover, a plastic cover, and it looks like this plastic cover, but it's made by rock. It's a roccia. It's a particular crystal, rock crystal, that is able to withstand, say, 1,000 degrees. So, for instance, this is used also for isolating the resistances in oven, in irons, for ironing the stuff. So, it's able to withstand very high voltage, but it's very fragile. So if you try to bend it, it will break. That's the reason why now they are using this kind of silicon pads, very thin pads, gray pads, that are using for isolating the chips. This is because actually some of these chips have, may have not ground, but the output or the input voltage on the central pin. And we'll see probably this later. I don't remember. Anyway, what actually do we need for using one of those chips? I'll show you the next page. The simplest situation is this one. You have an input voltage, you have an output voltage, X6, well, it could be 0.5, for instance, if you want an output voltage of 5 volts. The only thing that we need are two capacitors. One between input and ground, the other one between output and ground. You should use those capacitors. If you forget one of the two capacitors, usually what happens is that the system starts to oscillate. So you must always put those capacitors. By the way, what they are indicating here, this 0.33 microfarad and 0.1 microfarad, especially this one on the right, on the left, it could be a tantalum capacitor. Tantalum capacitors are expensive capacitors that have a good performances at low and at high frequencies, but they cost a lot of money. If we want to save money, instead of using one single capacitor here, you can put two capacitors in parallel. Typically, if you look at the circuit, you will find something like 100 microfarad capacitor with 100 nanofarad in parallel. That's a typical configuration. So instead of using this single capacitor, let me see if I can draw something like this. You put two capacitors in parallel. One is a 100 microfarad. Sorry, microfarad. I don't know if I can use this pen here. The second one, let me see if it works, is a second capacitor, doesn't work, of 100 nanofarad, and they are placed in parallel instead of this single capacitor here.
E quale tre?
Pardon?
Rispetto al 3, possibili al 3?
Sì, questo. By the way, actually this 100 microfarad, which is on the left, you can consider that is the filter capacitor of the rectifier. So if you have a rectifier on the left, this can be the filter capacitor of the rectifier. Then you probably need a 100 nanofarad capacitor that must be placed as close to the chip as possible. Why? Because the chip tends to oscillate at high frequency. If you try to filter high frequency oscillation with an electrolytic capacitor, it doesn't work. Because electrolytic capacitors are good capacitors, have large capacitance, but have very strong inductive parasitic behaviors in series with the capacitor itself. So this parasitic inductor will block the high frequency. While if you use a small, this is a typical ceramic capacitor of, say, 100 nanofarad, ceramic capacitor have very low parasitic inductance, and so they are okay for shorting high frequencies. That's why you can save money if you use the first electrolytic capacitor that maybe is already on the filter, and the second ceramic capacitor here. You see, this is the same capacitor that we can use at the output. We need this capacitor. If we forget this capacitor, it will oscillate. Here it says that although no output capacitor is needed for stability, it does improve transient response. Well, it can improve response. I can tell you that if you don't put one or the other two, it will oscillate. But they don't tell you, because otherwise you are scared that it can oscillate. You see, this tree is required if the regulator, let's place it as simple, is located at an appreciable distance from power supply filter. So again, because if we have too much distance between the rectifier, the filter capacitor, and the input of this chip, the wire, the long wire, will be an inductance again. And the inductance is able to induce oscillations. So you want to have a capacitor very close to the input of this chip. And so you will stop the oscillation. Sometimes you will find also a second electrolytic capacitor, something between, again, 10 and 100 microfarad, in parallel with the output of this chip. That is useful if your load is going to have a very high peak of current absorption. In this case, the large peaks of current absorption could reduce the output voltage of this chip, because the chip basically is a feedback chip. But if the transient is too fast, the feedback loop may not be able to correct the output voltage. So if you don't want to have a variation in the output voltage, you just put a large electrolytic capacitor in parallel with the output, and all the short and high current transient will be absorbed by that capacitor and managed by the capacitor. So you improve the performance of the circuit itself, okay? Then you can use this chip for doing whatever you want. For instance, you can create a current regulator, or you can increase the output current just adding an external transistor here. Or you can add the short circuit protection using the circuit here. You see, you can make a dual voltages also. They tried to implement any kind of circuit just because they want to sell you this chip. Okay, so you can do everything except for coffee, probably. But probably. What's more interesting is that if I want a negative copy on my voltage, instead of using this big complicated circuit here, I can use this one. I simply buy the 79115. 79115 is the mirror version of the 78115. So 78 manages positive voltages, the 79 manages the negative voltages. I want to show you something. Look at the number and the pins. Here we have the pin number 3. I want to use this one. In the 7815, the pin number 3, that is the central pin, is connected to ground, but is also the metallic part of the chip. In the 7915, the pin number 3 is the input. So this means that if you screw the metal case on the box, you are making a big short circuit on the negative voltage. In this case, you must use a spacer, an isolating spacer between the transistor, let's say, and the case or the heat sink. Otherwise, you are going to destroy everything. Okay. But this is very nice because if you want to make a dual power supply at fixed voltage, plus minus here 15, but plus minus 5, what you want, you just buy 7.8 and 7.9. And you can make a power supply. For instance, if you're going to use those chips for dual power supply in operational amplifiers. If you want to supply operational amplifier with plus minus 12, you buy 7.8, 12, 7.9, 12. And you can do a dual power supply with, for using these chips. Okay. If you are curious, you can download the data sheet of this chip, and there are a lot of information. Something that I wanted to show you. Sì, poi facciamo pausa. This one? Quali sono? Ok. Okay, I don't want to tell you things about that. There may be situations where there may be spikes of voltage, or something strange may happen also when you turn off the system. For instance, what may happen is that there are capacitors charged on the right part of the chip when you switch off the supply voltage on the right, when you switch off the part on the left. In this case, you are giving a positive or negative voltage from the output towards the input. This can destroy the chip if there are latch-up problems. Latch-up problems are those given by the creation of a PN-PN sequence that acts as a SCR, or how do you call it? DIAC. We call it a DIAC, basically. Yeah. So if you have, for some reason, if you create, there is in the chip the sequence of a PN-PN junction, we can go in latch-up. So it creates this sort of short circuit, and it can destroy it. Using this diode, they in some way are preventing this event. That is good, otherwise. But most of the time it can be also, yes, if we have a negative voltages, for instance, at the output for some strange reason. I don't know, from negative voltage from here that goes back here. So it may happen. No, the thing that I wanted to show you, if it is written, but I don't remember. I'm trying to see if it is written here or not. There is a minimum voltage for each of these chips. For instance, if you want an output voltage of 5 volts, if I don't remember, wrong way, you need at least 8 volts at the input. You must guarantee a minimum voltage drop on the series pass element for getting the good performance in the chip. So for 8 volts, you need at least, so for 5 volts at the output, you need at least 8 volts at the input. You need some voltage drop across the series pass elements in order to have a good regulation of the output. This voltage difference between output and the input is called dropout voltage. This is an old chip. In modern chips, what they tend to do is to reduce to a minimum the dropout voltage. So you can buy low dropout regulators which can tolerate a very low dropout. For instance, if you see here in this table, you don't see any chip able to go down to 3.3 volts. For 3.3 volts is the voltage that is used in some microprocessors. If they made this chip using this technology, for 3.3 volts, maybe you needed at least 6.3 volts or something like that as the input voltage. But instead, what you want is to derive the 3.3 volts from 5 volts. But in this case, you have 1.7 volts, which is not enough for this technology. While if you use a low dropout technology, you can go down. You can go down from 5 to 3.3 volts using those technologies. How it is made? Well, basically, they are not using a transistor, a bipolar transistor here in the series pass element. Maybe they are using a MOSFET. With a MOSFET, using some particular configuration, you can reduce the voltage drop across the series pass element. So you need to move to a different technology, more modern. If you look on the internet, there are thousands of low dropout voltage regulation. And there is a competition on who gives you the lowest dropout. I reached 1.1. No, I reached 1 voltage dropout, and so on. Okay. So they say, I reached 0. 0 means nothing, okay, but okay, there is no regulation. But it works like this. So they try to give low dropout. So remember this dropout. That is the voltage difference between input and output. Just very quickly, I want to show this, and then we stop. This is another interesting chip. Basically, is the same stuff, just with some small modification, where you can decide the output voltage just regulating two resistors which are placed between. We don't have any more the ground for some strange reason here. Instead of the ground, we have this adjust pin at the center. So you put two resistances, one between output and adjust, the other one between adjust and ground, and depending on the ratio of the two resistances, you can regulate the output voltage. And this is very good. Basically, this kind of circuit here was incorporated in the 78X6 series. So if you incorporate in the chip all the two resistances and you trim to a fixed value of two resistances, you get to the 78 series. Here, instead, they give you the possibility to change the output voltage. So actually, you can do a regulated output power supply, just for instance, changing the resistance R2. What is the formula? The formula is Vout is equal to 1.25 volts times 1 plus R2 over R1. 1 plus R2 over R1 is basically the voltage divider that we have here. Plus, there is a small quantity that you have to add that is due to the current E adjust flowing through this resistance R2. Okay. So with this formula, you can fix the output voltage. Just a question, why do they say 1.25 volts here? What is this 1.25? Band gap reference. That's the typical voltage for a band gap reference. So they're not using inside a voltage reference made with a Zener diode, but they're using a voltage reference. A band gap reference as the voltage reference, okay? So basically they compare this voltage that they expect from the input, and here something like 1.25, and then use this voltage divider for multiplying the voltage. Okay, this is very useful. For instance, if we go in the lab, we have some boxes with the breadboards, for those of you who attended the Electronics 1 classroom, and then we have on the side two very small power supplies which are incorporated in the box with voltage regulation. You can decide the output voltage. And they are using basically this chip. So you just trim with a knob, you regulate the R2, and you can go from 5 to 15 volts, something like that. Okay, okay, now that was the last slide for this part. I could start talking about the next block in this lecture could be the basics about signals. When I say signal, I'm talking about radio signals, because now we will start talking about how we can transmit or receive radio signals. So we'll talk about amplitude modulation, frequency modulation, and so on. But instead of doing that, we stop for 5 minutes. I would like to do something different, that is opening LT-Spice and looking something with you. At least for those of you who have never used LT-Spice, we can see how we can do simple circuits so that you will be able to start doing by yourself something. What I would like to do is to give you a number of possible exercises. You have to design something, and then you can simulate it. So those are some kind of homeworks. Okay, so you can take your time, but if you have problems, we can discuss about it. But that's because in other times, I hope to bring you to the lab, but at the moment, I'm not sure about the situation. I have very strong problems with your younger colleagues for entering the lab. So in the meantime, we do some good design and simulation, and then if you have time, we can try to play with the oscilloscope and other things in the lab, okay? So at the moment, we just stop for 5 minutes, and then we'll start with the LT-Spice, okay? See you in a while, okay? Okay, we are back. Okay, so as I told you before, we have only less than 30 minutes left. I wanted to show you something about this circuit simulator that is one of the many possible circuit simulator. But I like it because it's free and it's quite powerful. First of all, let me share the screen. This is the simulator that I want to use. I don't know if you can see it. If you want to find it, okay, let's start from here. This is the website of analog devices. The software that I would like to use is LT-SPICE. SPICE is a family of software. It's an acronym that means basically simulation, blah, blah, blah. That has been developed 30, 40 years ago. And of this software, there are many versions. Everybody can implement a different version. In particular, this LT-SPICE was implemented by Linear Technologies. Linear Technologies was a company devoted on fabricating very powerful, very interesting analog and power supply integrated circuits. They're not much on digital. There are a lot about linear circuit and switching circuit. In the last 3, 4 years, I don't remember, the linear technology companies was bought by Analog Devices. So that's the reason why now we can find these linear technologies devices under the Analog Devices company, and we must download it. It's very easy. You just search on the web LT-SPICE, and you go straight to this page. In this page somewhere you can download it. Download it. There are basically 2 versions. The version that I'm going to use is the LT-SPICE 17. The LT-SPICE 17 was developed for 64-bit systems. While if you still have an old XP system, you can download the LT-SPICE 4. That is more used for old XP systems. There is also a version for Mac, but I have to tell you the truth, it's not working as good as the version for PC. It has some limitations, the menus are quite different, and so most of the time people who have a Mac start the simulation, the Windows environment, and then install the version for Windows. There is a lot about this software you can find on the network, so on the internet, so it's very popular. And what is most interesting is that, as I told you, it's free. Why is it free? Because at the beginning, Linear Technologies and then Analog Devices have introduced the models for all their components, because if you first you try their components with LT-SPICE, then probably you will buy their components. So that's the reason that they supply this software for free, and it is very accurate, actually. So once you download it, it's something like 40 megabytes or 50 megabytes. It's not very large, very small. You can just click and install it, and you end up with something like this. I hope you can see it. It's the main screen, main display of this LT-SPICE software. The first thing to do, obviously, is to start a new schematic, for instance. So we go there, and you start the schematic diagram. Now the point is, who would you like to do today? First of all, I have to check with you. When I click on some windows like this, for instance, can you see the window opening, the menu opening? At home, I mean. Because it depends a lot on the fact that I'm sharing the whole screen of my PC. If you share only the window, probably we will not see that. So please tell me if you can see this menu coming down. Can you see them? Is there anybody connected?
Sì, professore, le tendine si vedono quando
Si vedono?
diciamo... Sì, sì, sì,
Okay.
sì, sì.
Perfect. Okay, grazie. Okay. Okay, so now the point is, what do we want to do with this software? For instance, we could start to simulate something simple, like what I used in the PowerPoint slides. I want to simulate a rectifier, the first stage of a power supply. If you see here on top, there are a number of devices. Some of them are very simple, so they're already there, but most of the devices are here in the Components tab. So you have to click Components, and click Components, you will see a number of devices. Again, there is this box here, where you have the basic devices, like resistances, basic transistors, so on. But if you want to go to something more complicated, you can go, for instance, in these folders, op amps. If I go to op amps, there is the whole production of analog devices, all the stuff that is called AD, means analog devices, plus LT, that was all the linear technologies library. So you have thousands of components this way. If you want to up, you go up one level here. So let's suppose that you want to simulate a rectifier, half-wave rectifier. Which are the basic components? First of all, we need a voltage source. Usually in a real power supply, you have a transformer. But today we don't want to go for something too complicated. We just use a voltage source, and we put it somewhere here. Every time you click, it gives you a voltage source. Okay. In this case, if I push escape, I stop copying voltage sources. Then we have to decide which are the performances of this voltage source. You see that when I click here, I move on the device, it changes from a cross to a hand. If I'm not wrong, just, yes, left click. No, left click doesn't do anything. Right click. With the right click, it tells you, it asks you to choose what is the DC value and the series resistance. But those parameters are good only for a real DC voltage generator. That is not what we want. We want a sinusoidal voltage generator. So we go to advanced here. And here you can choose a lot of different voltage generators. Let's go for something simple today. We just want a sinusoidal voltage generator, so I click here. And here we have some parameters to choose. What? Well, let's suppose that we want to simulate the mains power supply. Maybe it's too much, because with this power supply we are simulating the secondary output of a transformer that was connected to the mains. So here I would expect to find, let's say, 10 volts, a sinusoidal 10 volts voltage. So for doing that, I set the amplitude. I can say 10 volts. It's automatically in volts, you see here. And the frequency. Yes, amplitude, that's the amplitude of the sinusoidal expression. So it will go from plus to minus 10. That's the peak voltage. Remember that it's not the effective voltage. There is a relationship between effective and peak voltage. When I say 10, I mean 10 volts peak voltage. The effective voltage should be around 7 volts, because we have to divide the peak by 1.4. That is the square root of 2 for getting, and so it's around 7 volts. What about the frequency? 50 hertz. You write 50. The other parameters are special parameters that, for instance, we can have a sinusoidal voltage with a DC offset. So it is not centered around 0. but we want, let's say, 10 volts plus minus 10 added to a DC 5 volts. Instead of using two voltage generators and placing them in parallel, in series, we can define everything here. The other parameter is the delay. Delay means that not necessarily this sinusoidal voltage will start from instant 0. We can say that for the first second it has to give 0 volts and then it will start. So you can decide the delay. Theta, I don't know what is that. We can decide to start with the phase that is different from 0 degrees. You can start from what you want. You can also decide the number of cycles to do. If I don't put anything, it will give infinite cycles. Instead, if I want 1 or 2 cycles, I can write it here. Anyway, actually, it doesn't give you much help. But if you want to know more about this, first of all, I close it here. You can go to the Help menu, Help Topics here. Look for sign, for instance, search. Sorry that this is in Italian, but okay. You can do that. And then it will tell you voltage source. And here it will show you all the parameters of the different voltage sources, for instance. And let me see, that's a pulse. We are using the sign, yes. So it tries to explain you what are the different parameters that we can use. Anyway, that's a standard syntax for SPICE. So if you don't like what they say here, you can go on the internet and search for a SPICE tutorial, which has much more details. I also have some SPICE tutorial that I will share with you later. Okay, please remember that, otherwise I will forget. So in the Help menu, everything is explained really in a short way, but that just tells you the essential. Okay, that's a good start. We have a sinusoidal waveform with 10, starts from 0 volts, 10 volts amplitude, and 50 hertz. Okay. Now, the first thing that we must not forget is that when we do simulation, we always need a ground. So I take this ground from here, and I put it somewhere like here. If you forget, you see I clicked it just once, then I push escape, and I remove it. If you forget the ground, it will give you errors. It has to do with the algorithm that is implemented. It's like a division by 0, something like, or a matrix with a null element. I'm not sure about this, but anyway, it will give you errors. Then you can start connecting wires. For instance, you can connect bottom of the power supply with this ground. And okay, we can put some wire from here, for instance, to here. Every time you click, it's like placing a node. So you can, you see, oh, it's too reactive. And then escape again. Okay, if you want to move it, there's no way. I use this, that is zoom to full extent. If it's too much, zoom minus, or also you can use control and the wheel on the mouse, okay? You can zoom in and zoom out. Now what? We want to do, you said halfway rectifier. So you need a diode. Okay, this diode is rotate pointing towards the downwards. How can we rotate it? Once you select a component, you can use Control R, and you can rotate it. You see, every time I push Control R, it will rotate. For instance, I can put it here. A second diode, I don't want a second diode. I rather want a resistor, that is our load. I can put the resistor here, for instance. See, every time I click and then I move, then I zoom out, and I want to connect the different components. So from here to here to here, and then the resistance. Well, I can put another ground here, or if you want, I can connect it to this point. You see, it will generate automatically a node here. We are okay now. If the point is that I have not defined the diode. Well, in this case, this is a generic diode, but the resistance R has no value. So first, I want to change the value of resistance R. Again, I move on the resistance. It shows the hand. Right-click, resistance. Well, we can put, say, 100 ohms. If I don't say anything, it's ohms. Then, what about the diode? Again, I can choose a generic diode, but I prefer to choose a new diode, basically change the properties. So I can take some commercial diode. Well, for instance, I could use, what are those diodes? These are, this 1N4148 is the same as 1N914. Those are signal diodes, so for small signals. In this case, I will use something more powerful. You see here, those are the specification. Well, average current is 200 milliamps. It's a bit weak. I would use something more powerful. Let me see if there is something like, for instance, 1 amp. Those are all Schottky diodes. I want to select silicon diode, so I click on type. I will list all the silicon, first the Schottky and then the silicon. And let me see if there is something more powerful. Like, I don't know, we can take this. MURS 120 on semiconductor, silicon diode, breakdown voltage, reverse breakdown 200 volts, and 1 amp. That's a good diode for a power supply.
Why did we select this one?
Because otherwise, no, I like the output current, 1 amp. Okay. The other one, if I leave the generic diode, it's something that has not well-defined the properties. While this one is a commercial diode. So I prefer using commercial devices instead of theoretical devices. So, okay. I think that we have all we need for this. So 10 volts, blah, blah, blah. Okay. Now we have to start the simulation. I can click on run here, or I click on simulate, and we have run and control panel. The first time you run a simulation, so I click on run here, will show you the control panel. Because it needs some more information. Practically, it wants to know how long the simulation has to last. We have a 50 Hertz waveform. So 50 Hertz means that the period of this 50 Hertz wave is 20 milliseconds. For instance, we may be interested in looking at the first 5 cycles of this simulation. This means that I want to stop after 100 milliseconds. How can I say millisecond? Just M. Okay. Please consider that the system is case insensitive. So if I write M, this means both uppercase or lowercase means milli. If I want to use mega, I don't write M, I write meg, M-E-G. Okay, that's mega. The other multiplier are milli, micro. Micro, for writing micro, use U. So if I want 100 microseconds, I will use 100 U. Okay. Okay, then some other parameter. Time to start saving data. You can decide to skip the first tot seconds and then start later. We don't care. Maximum time step. This is interesting. What is this? The simulator is kind of a lazy simulator. It doesn't want to do many calculations. So we'll try to do less calculation that it can do for reaching the result. But if it doesn't do many calculations, probably the output will be a line that is not very smooth. While if you have an idea of what is the speed of our circuit, we can force the system to do smaller steps. For instance, we have here a sinusoidal waveform that lasts 20 milliseconds. Okay. So why don't we force the system to do, let's say, one step every 20 milliseconds, 20 microseconds, for instance. So one single wave will be described at least by 1,000 points. For instance, I can say that the maximum time step will be 20 microseconds. You see, 20 U. At this point, now we also do the steps. Actually, the system automatically adapts the speed, the time step, depending on the slope of the output waveform. But it tends to do not many calculations. So now we force to do at least 1,000 calculations for each wavelength. Okay, then, okay, the moment we skip all other parameters, okay, and that's it. It has already done, let's say, 5,000 simulations. We didn't realize that, but it has already done the simulation. The point is that we have this plot, but we did not indicate what we are interested in. For instance, I want to check if the sinusoidal waveform was correct or not. I go here. You see that a red probe appears. If I click on this node, it will show me the waveforms. This is the waveform of node 1. The only problem with this software is that it does not show the node name unless you go with the probe, and you will find in the bottom, look at this part here of the screen, it will show you that that's the node 1. So at the moment we are plotting the node 1 voltage. I want to show also the voltage on the output node. By the way, all the voltages are referred to ground. So that's why it's so important that we have a ground indicated perfectly there. If I click with the probe on the output resistance, it will give you the voltage of the output resistance. I click here, and it will add it on the plot. This is something that we have already seen. Basically, we have a half wave output with a blue line. That's the plot of voltage on node 2. Node 2 is this one, yes, because it's written there, node 2. And if you see here, there is a reduction between the maximum voltage and the input sinusoidal wave voltage and the output voltage. If I try to zoom, I can do that here, like this. I go to the, first of it, I have to select the window, top window, then I go to zoom, and I can zoom here. You see?
Nel caso in cui bisogna rifare la simulazione perché si è messo un dato sbagliato, perché allora il controllo è secondo.
Okay. Your colleague is asking what we should do if we have made some wrong data. First, you have to go to simulation. Sorry. You have to click on the bottom on the schematic.
Okay.
Then you go to simulate, control panel. You check on this. Sorry, not that. Edit simulation command. This one. Here you can change the parameter in the simulation command. Okay, and then you do run again. Okay. Now instead I am here on the top display, the one that shows the waveforms. If you see here, actually there is a voltage difference between the input and the output. That is the knee voltage of the diode. How much is that? I can zoom further. I go like this. We are on the peak of the positive waveform. How can I check that? Well, let me try with the right click. No. I have to right click on the node number. Oh, no, like this left click. If you see, there is a panel appearing here that shows you the position of this slider. Okay, we are at the peak here. That's the slider 1. And this point, the voltage is 9.98, it's 10 volts basically. If I want to check the voltage difference, I left click again on the second voltage. And now I have a slider, should have a slider on the other voltage, but it's not working. That's interesting. And okay. No, I can do that. So this is the slider 1 and cursor 2. No, to this one. I don't remember. That's cursor. Okay, let me do this. I clicked two times on the green line. So I have cursor 1, and now I have cursor 2. And I'm not sure if I click on B2 and that once. Okay. I have cursor 2 on the top voltage and cursor 1 on the bottom voltage. You see that is going down. So you have to play a bit with this stuff. I don't remember either. Yeah. Okay, now the voltage difference is here. You see vertical difference between cursor 2 and cursor 1, 6.61 millivolts. That's the knee voltage of a diode. The 0.6 or 0.7 volts that we say is the direct voltage in a diode. And so actually we verified this. And it's just 1 minute left. Let me go back here. I want to go back to the previous zooming. Prego? Hello?
Ha fatto tasto destro, quindi su...
no, tasto sinistro. I clicked two times with the left click on one single volt, and then I clicked once on the other one. In some way, it will move the one cursor from the one to the other, okay? So it's a magic, but it worked. Okay. Now what I want to do is to go back to the previous zooming. So I zoom full extent, and I get the whole wavelength. I also remove the cursors, click on here. I want to show you very quickly what happens if we add the capacitor to this circuit. So I go back to this window, I take a capacitor, I put it here, okay, escape, then we connect the capacitor. So we are adding the filter capacitor to the circuit, oh, sorry, and again here, from here to here to here, okay. Then what? I have to escape, and with a right click, I have to change the value of the capacitance. For instance, we can put 100 microfarads. I don't know if this is okay. Or 10 microfarads, which is better. 10 micro, and that's our capacitor. Well, obviously, the system has not done the simulation yet. So if I want to do a simulation, I simply go again for run. I don't change any parameter at the moment, and see what happens. Okay. Well, what I see here is that the capacitor is too small. You see that it doesn't, it charges, but then discharges very quickly. Let's try to increase, okay, to a better voltage. So 10 micro, well, simply to 1000 micro. Now it should work. Again, the simulation. Okay, now it works. Okay, now that's the code. I may be interested not in the voltage, but in the current. Current. If I move here on the wires, I have the voltage. But if I want the current, I move the cursor to the device. You see that there is this kind of strange, okay, I'll do this here. It's too small. Anyway, it's what they call an amperometric tester. So if I move here, I can check the current through the device. I click here, and see.
Noi questa cosa non la vediamo, quindi praticamente abbiamo cliccato semplicemente sul condensatore e spunta di un simbolino diverso, a quanto pare, poi cliccato sul condensatore.
No, I clicked on the diode. Ok.
Ah, ok.
Non vedo il simbolo. No, è un problema del display, da un Teams. In Teams non fa vedere i cursori, non fa vedere le... Okay, so you see here This is a graph that you already saw in the slides. Basically, the red line now is the current through the diode. Well, the first time we start with the first cycle, due to the fact that the capacitor is fully discharged, we have a very high peak of current that is needed for charging the capacitor. Then we have the discharge of the capacitor, so the next peak will be much smaller than the previous one, because here the capacitor is already charged. So the peak current, the current peak is lower than the first big current peak. You see? Okay, that's just an example of what kind of simulation we could do. The next time we will try to simulate something, or also what I can do is to give you some circuit to simulate and try by yourself to do the simulation. And then if you have a problem, we can check them together one of the next days, okay? So at the moment, just start downloading and installing the software and start to play with it. So the more you play, the better it is. Okay, so see you on Thursday. Bye-bye for today. Arrivederci. Bye. Arrivederci. Arrivederci.